We will continue with next talk with Jan Margeta, who will tell us something about physics simulation. Yeah? Okay.
Correct, yeah.
So please give him a warm welcome, warmer than this room is, please.
Hi. Have you ever noticed how some sounds sound like fun? Maybe the sound of your chocolate bar when you crack it open, and or maybe the roar of a lion at a nearby zoo. Imagine a world where you couldn't hear these things. That's what it is like for some of us. But there is a special kind of surgery that can help and restore part of the hearing. It's called cochlear implant surgery. So that means inserting an electrode into the cochlea to stimulate the cochlear nerve or the auditory nerve. Now, what is a cochlea? Think of it like a little snail-shaped organ inside of our inner ear, that's over here. It's roughly the size of 1 centimeter. And the electrode has length of 2 centimeters. So now imagine that you have this small organ that's just this size, this is 10 times the size, and you want to fit a wire that's 2 centimeters long into 1 centimeter long organ. Fortunately, the cochlea is a spiral, so it spirals and you can fit it in. But it's not only about fitting it in, it's also about to achieve the desired depth of insertion. Otherwise, this restoration would not be complete. You would not be able to hear some frequencies, you would hear distorted sounds, and so on. So before the doctors do this surgery, they plan. They use these super cool tools, like the one on the screen right now, where they take images of the patient, like the CT images that you see on the top left, and do some image processing parts and extract 3D models of the cochlea. And so then once they have the 3D models of the cochlea, then they can plan how to get in and insert to the proper depth without hurting the patient. And well, each cochlea is unique, so we need to repeat this for every patient. And so that's where physics simulation comes into play. Physics simulation is like building a digital twin of the real world that accurately represents all the important aspects of the world that you want to model. So for us in this application, it serves as a virtual playground for the surgeons to try different insertion strategies or different insertion devices, and whether the spot of insertion is the right one or not, so that the patient can hear the best. For gamers, it's kind of like playing a video game, but instead of killing the aliens or something like that, you want to fit a wire inside of the cochlea and see where it ends. So here's a little example from a collaboration with the University of Lille, INRIA, and Optical Medical Company, where they developed an active cochlear implant and tried to compare that to the passive cochlear implant. So passive cochlear implant, as you see on the left, is this wire that tries to get into this snail, into the cochlea. As you might see, at some point, it starts to scrape the wall of the cochlea. That's not desirable. So there is a new device that, thanks to simulation, can happen where instead of scraping the wall, you use active controlled cochlear implant where you apply a little electrical current on the implant, which lets it bend inside of the snail. So, hi, I'm Jan, and why I'm telling you all this? I've been Pythonista for many years. I did a Master of Science in Computer Vision and Robotics. I did my PhD in medical imaging from INRIA, MinPyTech, and Microsoft Research. I'm a founder of a company called CardioMe, building medical imaging software, like the one before. And I'm researching technologies for human hearing with Optical Medical now. So it's a lot of vision. I've been doing a lot of vision over the last years, but I did vision and robotics. Maybe it's time to go back to some hardware, to do some robotics again, at least digitally. So yeah, doing simulations, robotics, and so on in Python, yeah, we kind of know that Python is not the fastest language around, so it doesn't really make sense, does it? So shall we do actually simulations in Python? Well, lucky for us, there are many ways of, so don't despair. There are many ways of doing simulations in Python, and we'll cover a few. There are libraries available. So which physics simulators do we talk about? There are multiple ways of simulating physics. There's this multi-physics aspect where you simulate multiple different areas of physics, essentially different phenomena, and try to put them together. There are frameworks like SOFA framework or PyChrono. SOFA itself is built in C++, and so is PyChrono, but they have both a nice wrapper for Python. If you are more interested in like robotics, then don't hesitate to look into things like Mujoko or PyBullet. Although Mujoko was built for robotics in mind, PyBullet was built as a game engine. So the physics simulations are not necessarily the most accurate, but they're fast. And there are also some applications about soft robotics. Exactly like you saw the electrode array going inside of the cochlea, which bends. And that's an example of a soft robot, which you can steer and so on. So if we go first to the SOFA. So what is SOFA? It's this multi-physics tool that has an extensive plugin system. That means that you can simulate all the different aspects of physics. And if anything is missing, well, you can code your own. It requires some C++, but you can do it. It's a simulation through this visual tool. So you open the SOFA application and you load a scene. We'll talk a bit about the scene later. Then you simulate and collect the outputs if needed. It's a tool built by INRIA in France, and it has a powerful support behind it through its own community. So how do we build models that can simulate physics in SOFA? There are two ways. One is to define an XML scene, and the other one is to define the same XML scene, but in Python, and then it kind of gets converted to something that looks like the XML, but that happens to be behind the hood. So let's see how the scene is. So a scene is nothing more than a kinematic tree, as you might know from other areas. It's a tree of nodes, and each node has some behavior. So a node can be, for example, this room is a node, is a root node, and inside of the room there are people around. Each of us is a separate node that's a child of the room, and we all have properties. We have our own weight, our mass. We sit on the chairs, so the chairs are nodes, and we and the chairs. There is a force happening so that we don't fall through the chair, which is a collision, or there's a force happening on both sides. So you need to define the scene in SOFA first. And how to do that in XML? Well, as I said, there's a root node which is responsible to defining the time step of the scene. Of course, it's not a continuous simulation, so this world is discretized. The world which we can simulate doesn't happen like smoothly, but based on the phenomena, we know that, for example, some things are not going to be quicker than some time, maybe 1 microsecond. And so we can discretize the time step and do, if you had any differential equations in school before, this is where your delta essentially is. So we define the roots of the scene, and then we want to also specify the time step. We define the animation loop, which is responsible for running the simulation itself. Some objects, which in SOFA are called mechanical objects, and we assign it properties like degrees of freedom. What degrees of freedom mean is like how many things, what is the dimension of the state that this is attached to the object. For example, me as putting this cochlea on this desk, it has 3 degrees of freedom normally in space, but here it would have only 2 because it moves in plane. And it might have a rotation, so it would be 4. But in 3D, it would be 3 rotations and 3 positions, 3 translations. Then we define how to solve the system, which, again, you might remember some Euler integration or some Runge-Kutta, and so on. So you define these things like Euler, and then a solver, which like in this case would be like a conjugate gradient, like how to solve this system of equations. And well, all the objects doesn't have to be only like rigid. You can assign it other properties like stiffness. So you can simulate the different elastic objects. You can simulate, for example, propagation of electrical current and so on. So all these things can be defined. How to do it in Python? There is a library called SOFA Python 3, which is a low-level, very low-level API to access all this. And you need to define a lot of things yourself. That is an advantage that you are completely flexible to define anything you like, but at the same time, it's maybe not the best way to start coding in SOFA. That's why there's also another higher level API built on top of that, which is a SOFA template library, for example, and the standard library, which helps you to reuse prefabricated elements so that you can then define like basic building blocks, like loading meshes, loading geometrical objects that are standard, and giving them properties like defining the collisions and so on in a simple way. I invite you to read the documentation. It's a fairly well done. Of course, it has its own issues, but it's a very nice library. So if you want to go a little bit beyond what SOFA offers, you have the plugins. And one of the plugins is a plugin for simulating soft robots. Soft robots are actually the continuous robots, which don't have a discretized set of operation, but they're slightly different from the ones you see in car industry, where you have links joined physically together and everything has to move rigidly from one place to another, and then you compute the forward and inverse kinematics to know. So forward is that you know what are the orientations of the angles of the joints, and you project it to the position, so to the XYZ of the end part of the robot. The problem of inverse kinematics is that you have the XYZ position of the robot, and you want to know what are the joint angles that the robot has to achieve to get to the position. That kind of works well enough for rigid robots, but it starts to be tricky for something that's soft. And that's where the plugin Soft Robots and Soft Inverse comes into play. And I would like to highlight that the current way of producing soft robots gets us to a more approachable way of doing it. It doesn't require much, but a little form, a little mold, which you can fill with some rubber, let it cure, and glue together, and then have a bit of a compressor or something that helps you move things around, to inflate it and move around. So I do hope that these kind of tools will help us to explore a little bit this avenue. The other advantage of simulating physical objects is that you can play with things a lot, and it's cheap. You can construct things, change parameters, tweak them a lot, destroy them. Does not hurt the patient, does not hurt the thing, and of course, you don't have to have the physical thing at home. So for example, if you're an architect or some engineer designing some beams, some structures, there is a plugin that will help you to design the properties of those beams. So if you can parameterize your beam, like what is the height, what is the width of the beam, and so on, you can run the simulations, multiple simulations, thousands, millions of them, and see where are the weak points, and simulate the forces around the beams, for example, like here. And so the design optimization plugin is a very helpful thing to do that. But it would not be as good without the really, really nice library that's called Optuna. There's a Python library for zero gradient optimization. There's a Bayesian optimization that helps you find minima of a function that are not necessarily differentiable. So if you ever have any function that you want to optimize for, and you have some set of parameters, give Optuna a look. So SOFA is powerful. It has all these features. And I think that SOFA itself is probably likely the most complete open source physics that you can find in Python. You can simulate pretty much any aspect of physics, and if anything is missing, you can write a plugin. Of course, you need to know a bit of C++, but it's doable. So if this is a bit too much and you don't need all this flexibility, maybe you want something simpler. Maybe you have some robot that you want to control, and or a little toy car that you want to play around. It's not only for toys though. There is a MuJoCo framework. So MuJoCo itself used to be a commercial solution that was acquired by Google DeepMind in 2021, and Google made it open source. So the advantage of MuJoCo is that it's fairly well contained. It's not as complete as SOFA, but it lets you simulate things fairly well, especially if you're simulating objects with joints and contacts. So for example, like a robot walking in a room. So it's touching the ground, it's making contacts, and you want to see whether it's stable enough. It has well-defined dynamics, and it, as I said, is maybe not as complete as SOFA, but it starts to get all the components now. So it's not only for rigid things, but it also gives you objects that can define flexibility, clothes, ropes, and so on. So the idea of making a scene for MuJoCo is very similar to SOFA. You construct the scene or a kinematic tree where you attach coordinate frames to each other. So you start with some root node, and to the root node, you start to attach parts that move together. So for example, a root node, if root node is my body, my arm is another reference frame, and my elbow is another one, so the hand actually moves together with the rest of my elbow and so on. So you can get more and more detailed. And so these things are computed for you. So that's why you see how well it works for robotics. To simulate things, you can run, again, like the scene, which you define in XML, and it looks pretty much like this. So this is a simple object that is defined in this XML format. There's a root called MuJoCo, and you define some assets, some bodies, and things that move around. For example, if you have this Python logo, which is free falling, you define it as a free joint. So there's this concept of body here. So the body itself is one object that is in the kinematic tree, and that has its own property. So free joint means that it can move freely in the scene. Although you can also give it a joint that is not free, that moves together with some arm, some hinge, for example. So you load the scene in, also you can load the scene from Python to simulate it. So you can define you can define a scene, make it run, and well, what would be the point of running a physics? Is not only a pretty visualization. Of course, you can use it in your physics classes, but also, once you have the physics simulation, you want to measure things. So each of those nodes has properties which you can then read during the simulation. So for example, here we have a little example of running the simulation for 3 seconds. And the important bits are that we have this MJ step function, which evaluates the model and moves from one state to the next time. So what happens from now to the next delta t that we have. And once we have that, we can then measure what's happening. So for example, for the Python logo falling, because that's the only thing it can do, is in empty space, there's gravity pulling. So you might remember that there's just acceleration caused by the gravity, and it goes down until it hits the bottom, the floor. If you're really Python purist, there's a way of defining MuJoCo models in Python. There's a nice tool called DM control, which lets you do that. Although DM control has many other things to help us, I do not personally recommend using it to define the Python models. What actually worked better is the XML format that's over here. But if you add a little schema over here, you get all the nice code completion in your code editor. And I think that's super powerful. So, but maybe you don't want to define your own models all the time, and you want to use something pre-trained. You want to play with the robot. You want to try some new machine learning techniques, some reinforcement learning algorithms to try to control these robots. So there are libraries, collections of environments, which, for example, is Mujoko Menagerie, which is a collection of pre-built models which can use right away. And these are exact copies of what you can buy in a store. There's a KUKA robot, for example, or the Atlas robot, or the dexterous hand. So how to control these models, though? So you have a model. Let's get a little bit mathematical here. Because you have a model and you can move the joints around, but like how to reach the position where you want to be and so on. You can compute the inverse kinematics, inverse dynamics, and so on to control the positions of the joints. And yeah, you can. And that's the state. So the angles, the angular velocities and so on of the system are the states of the robot. And so how do you move from place 1 to place B? Those who did automation from us, there is a way of doing it with control theory. So if we are able to define some state transition matrix, which essentially tells us how to get from time 1 to time t plus 1, that's essentially telling us the dynamics. Like what happens if I'm here, I apply this input, and where will I be in the next step? So this is what happens. This is a linear time invariant system where A and B define these matrices. X is the state, and Y is the control input, or the sensor values. And so now we have this, usually we have some feedback loop, which from the outputs, we want to find out what shall we change in our control to reach the target goal. In other words, there's this matrix K that multiplies the input, the state, and that tells us like how much shall we move. So you can see it like if I have a pendulum and I'm too far away and I want to bring it back, I have to maybe move a lot, so that the control signal has to be large. If I just need to move a little, then the control signal will be small. But so how do we compute this feedback gain? This is probably my most mathematical slide over here, and it's essentially one way of doing it is computing some regulators, like the linear quadratic regulator. So it's an optimal control over some fixed time horizon. What does it mean? Like it sounds maybe too much. What this means is we want to find some action that will bring us to some target while not spending too much energy, for example, over time, so like, and how quickly it will get there and so on. So we can balance things. We can balance that maybe some joint positions are hurtful to the robot, so we can penalize them and so on. But that all needs this A and B. So if you remember A and B, the state of the transition matrix, the two matrices over there. So this is fairly painful to compute often, especially if you have a nonlinear model. But here with Mujoko, you can do MJD transition FD, which linearizes the model and computes with fine differences the A and B at the current state. And once you have the current state, you can then find decay, finally. It's a solving algebraic Riccati equation. And you might remember from your school when you used MATLAB for that. You don't need to use MATLAB. We are in a PyCon conference here. I think we should all switch. So if you don't want to go to too many tools, there's something already in SciPy, which is called solve discrete ARE, which does it for you. Then you need to do some matrix multiplication. But there's even something better. There is a Python control systems libraries. And if you ever used MATLAB control system toolbox, this is a very good alternative to that. It's purely in Python. That is very understandable and readable. So don't hesitate to look into those tools. And if you want to have a better tutorial on the LQR, linear quadratic control regulator, there are ways to do it with Mujoko. And people interested in MPC or model predictive control, again, there's a tool for that. As another alternative, if you don't like control system theory that much, and you're more experimental, and you want to do learning, because maybe some things are just a bit too hard to control. And maybe some things are not linearizable enough to be able to compute the A and B matrices. So let's go to reinforcement learning. Reinforcement learning is this way of, given some state, you have some agent that walks around the place. It observes the space. And it estimates what is the state of the space. Well, state means that, I don't know, I have my cochlea over here and I have my robotic arm over here and I want to find the angle and I then see, oh, the cochlea is here, my angle, my robotic arm is like here and I want to change the direction here. So the state is I'm here and the target is like, okay, given this state, what is my next action to make? Move right, up, down, left, right, orient, turn, and so on. So it observes the environment and does the action, and then reobserves the state, and so on, and so on. The advantage of our ecosystem in Python is that we have great tools. We don't have to develop your reinforcement learning algorithm. There are many. And it gets very simple now. Oh. It's very simple now. It's almost like a scikit-learn interface that is to open like this baselines library. I don't know what you see, but it's changing things so much for me. It's probably the physics. Getting there. So what if we do this? Okay, it's not exactly what I see, but it's fine. So you need to define some environment where you measure the state and then you want to do some action. And there is this consistent, unified way of doing that. And there are plenty. I'll let you explore and choose. So you can then play with many different examples. And there's our conversion tools too. And now when you have the little environment, for example, here's the cart pull controller, which essentially it's a cart that's moving on a line and it has to balance an inverted pendulum, a little line with a little lever that's attached rigidly to the bottom. You can define this kind of environment with Mujoko. But here is a little simpler example. We're using simpler physics. And it doesn't require more than a line of code to train such a model. You observe the state, you do some observation, you do some reward, and you reiterate. What is the reward? Yeah, you want this thing to stay up, to stay alive as long as possible, and you don't want to move it too much. The observation, it's what is the angle with respect to the ground. You want it to be straight up, so 90 degrees up. And also you want to measure what is the current position and what's the velocity to estimate the next action, whether to move the car to the left, to the right, to balance the pole. And so after not many iterations, the pole that used to move like this, so whenever you see a little jitter, is when the environment resets. Essentially, the pole fell. After like 15,000 iterations of this thing, you get something that's fairly stable. So you can start controlling your environment with reinforcement learning. So that's all in the simulation. And if you want to close the gap between the simulation and the reality, which of course no simulation is perfect, then there are tools that help you close the gap. The tools are usually in the domain of sim to real transfer. Essentially mean you simulate a lot, you change the environment a lot, so that it covers all the different appearances of the real world. And once you have that, then maybe your tool, your robot, your controller, is better adapted to the real world. So some tools that I would recommend in this domain, like the control system library as a great replacement for the control system toolbox in MATLAB. The robotics toolbox, which some of us remember Peter Clark's MATLAB robotics toolbox. So this is, again, Peter Clark doing it in Python. I think everyone is moving to Python these days. And some other libraries that might help you in this domain. So if we go back to the cochlear implant surgery, so the robotic simulation, the digital simulation of the implantation might help us to better plan for the surgery, to better estimate the forces that are exerted on the cochlea, to better determine the angles at which to enter, and maybe better choose also the implant type that goes inside. And in turn, help the patient hear better. So I wonder, what are your applications of physics? And the boom of robotics is here. It's totally inevitable that these things are coming. It's not only about software these days. We need to get into the hardware too. And I'm really happy to see that there is a community of learning with hardware with us. So this is the moment where we can get in touch with hardware and do some cool stuff. And I wish you good luck and hope that we do build something really, really cool. Thank you.
Thanks. We have some questions.
Good.
Thank you for your talk. Very interesting topic. I will start with the simple one. Which framework would you recommend for thermodynamics simulations?
SOFA. SOFA is the best for this kind of thing. Of course, if money is not an issue, well, ANSYS is the commercial solution that's still likely the best simulator, but SOFA is like the second best.
Thanks. Would it be possible to set up simulations to automatically find the ideal ways to insert the fire in the cochlea, or automatically invent the optimal shape? Okay. Not really. Okay, what would I take for machines to be better at these tasks than humans in case they get all the context?
Yes, exactly. That's where our partners in Lille and at INRIA and the University of Lille are doing. They're designing new implants that should help us with that. Yeah.
Okay, so it is theoretically possible to invent that. Okay.
The tricky bit about cochlear implantation is that getting into the cochlea is not easy. You essentially drill behind a hole behind the ear that goes straight to the cochlea. There's a really narrow passage. You don't want to hurt the nerves. So there's the facial nerve and the so-called chorda tympani. If you hurt chorda tympani, you lose a sensation of taste. So you definitely don't want to have life without taste. And so you need to get in between. And so having a curved robot is not easy to get in. So, but there are ways of handling that.
We will wait for Star Trek nanobots that will get there by themselves.
Yeah, maybe.
Okay, say using these open source libraries, I develop some hearing or vision aid solutions only digitally. How do I proceed from there? What's the process or steps from creating solution until doctors get to implement? Years of regulations, approvals, MDR, go on.
Yeah, MDR is a fun regulation for medical devices that we have in Europe. In the US, you have FDA regulation, which but I think it's doable. Like currently, then you have standards that can help you follow that to develop these kind of devices. But also, of course, it's not easy. The whole thing of validating this is really hard. So you start with digital models first, then you go to some animal models, then you do cadaveric models, and only after extensive validation you might move to human specimen.
Thank you very much. I have some. Okay. More questions? No. I have some notes, know-how, how to use the lunch thingy. Yeah, you go to lunch. First, there is in the bottom, in the right corner, there's actually soup. A lot of people didn't know about soup. There is soup. You can get soup, and there is a short queue usually to the soup. You get the soup, you start to eat it, yeah, and then you can stand also in the other three lines. There are a few other queues that you can get to the normal main meal. So in the meantime, you can eat the soup, yeah, or you can just sit down there and have in half an hour. Eventually, you can also, when you get the food, you get also outside. There is you can go to the terrace, etc., etc. Thank you very much, and have a nice lunch.